Alright class, this is chapter 3.3 lecture. Make sure you have your notes up, I'm sure you do. Here we're going to talk about piecewise defined functions and power functions. Piecewise defined functions typically scare most people, but don't let them scare you. They're not as hard as they seem. So I'm going to start us out with an example. So in this first example here, it says postage paid for a first class letter jumps by 21 cents for each ounce after the first ounce, but does not increase till the weight increases by 1 ounce. So table 3.5 gives the 2015 postage for letters up to 3.5 ounces. Write a piecewise defined function that models the price of postage and graph the function. Okay, so typically a piecewise defined function f of x looks something like this. Okay, so what you get here is if your weight is between 0 and 1, your postage is going to cost you 49 cents. So your f of x, which is the same thing as your y here, would be 49 if 0 is less than x is less than or equal to 1. And sometimes they write for instead of if. Either's fine. It's 70 if 1 is less than x is less than or equal to 2. It's 91 if 2 is less than x is less than or equal to 3. And it's 112 if 3 is less than x is less than or equal to 3.5. Alright, so we've got the function actually kind of drawn out. What we need to do now is actually draw the function. Okay, so if we've got our graph here, just going to do a rough sketch. Okay, so your x values here, we're going to look at 1 to 3.5. So I'm going to do 1, 2, 3, 4. Okay, and of course there's a 0 right here. My y values go from 49 to 112, so I'm going to go by 50s. So this is going to be 50, 100, and then 150. And this is just a very rough sketch. Okay, so if we're looking at our function, it's going to be 49 for 0, from 0 to 1. So at 0, we have an open circle all the way to 1, and then we have a closed circle on 1. So it looks something about like this. It's a little bit below 50. Like I said, I'm just doing a very rough sketch here. Now from 1 to 2, we're at 70. So 70 is about right here maybe. So I'll do an open circle here all the way to 2, where I'll do a closed circle. Now for 3 it's 91, so a little bit closer to 100. And we'll draw the line here and draw the closed circle here. And from 3 to 3.5 is 112, so a little over 100. So open circle on 3 because it's not equal to, or 3.5, and closed circle on that 3.5. So your piecewise defined function approximately looks something like this. A lot of people call it a step function because a lot of times it looks like a pair of stairs that you're walking up. That's simply what a piecewise defined function is. You graph each one of these little sections piece by piece, and their conjunction of all of them is your entire graph. So let's look at example 2. It says graph the function. We've got f of x equals 5x plus 2 for 0, it's less than or equal to x, less than or equal to 3, and x to the third for 3 is less than or equal to x is less than or equal to 5. So what we really have here, let's try to sketch this out a little bit. Okay, we're going from 0 to 5 essentially. So there's no need when you sketch this graph to have a whole big side of negatives. So we'll start the sketch here. Let's see, what do we need to go by here? if I'm looking at the first equation, I know I have to plug a 3 in it on one side. If I do that, I'm going to get a 15. 15 plus 2 is, let's see, that's looking like 17, and then 5 to the third is 125, excuse me. So let's go by, I don't know, let's go by 25s on the upper one, and we'll go by, obviously, 1s here. So 1, 2, 3, 4, 5. Okay, here I'll go by 25s. Don't really need to go to 150, but we'll go there anyway. Alright, now, let's see, let me just graph it in blue. So, if I'm looking at this, I've got 5x plus 2 is my very first one. That's a straight line, okay? So 5x plus 2, that's linear. So, really, I can plug in a 0 and I can plug in a 3, have 2 points, and generate a line. Okay, and if I plug in 0, 5 times 0 plus 2 is just equal to 2. So my first point here is 0, 2. So it's somewhere down around in here, in this area. Okay, I'm going to plug in the other endpoint here. I always plug in my endpoints. You have to plug in your endpoints. For a linear one, like this one, 5x plus 2, you really only need 2 points, so just plug in your endpoints. It's equal to 0, so therefore that's why I have a solid dot here. Like I said, if I plug in the 3 here, 5 times 3 is 15, plus 2 is 17. So if I come over here to 3, it increases to 17. So what I get is a solid dot there because it's also equal to, and I just connect the 2 points to make a line. Okay, so that's approximately the first part of the graph. If I look at the second part of the graph, it's a cubic function, which means I'm going to need more than 2 points to kind of figure out how my line goes. Okay, because it's not a straight line here, it's got some curvature to it. I'm still going to start with my endpoints. So 3 to the third, that's 3 times 3, which is 9, times 3, which is 27. So if I come over here to 3, I need to go up to 27, which is actually probably somewhere right here. Okay. If I plug in 5 to the third, like I said, 5 times 5 is 25, times 5 is 125. Okay, so I need to go up here, 5 and up to 125, which probably somewhere right here. Now, like I said, this isn't a straight line, it's a curve, so I'm going to need to at least do 3 points, maybe even more. Let's look at 4 to the third. Okay, 4 to the third, 4 times 4 is 16, times 4 is, what, 64? So let's plot that point as well. So 64, not quite at 75, not quite at 50, so we wind up about right here. You can see that kind of generates a small curve there. Okay, don't want to go past the point, so it kind of erred that a little bit. But it kind of generates this small looking curve here, and I know I'm not doing a great job of doing it. I'm trying to make it look a little better and probably just making it look worse. But this part is a kind of a curve like that. It's not a straight line. This is a straight line. This is a curve. And this is the graph of this function. So hopefully you kind of followed how I did that. It's not really hard. Just do it piece by piece. So we took the first piece, we graphed it within the domain. We took the second piece, we graphed it within the domain. And there it is. Okay. Let's scroll on down to page 2. Okay. This one says the cost of weekend service calls by AirTech Services is shown by the graph in figure 3.27. Write a piecewise defined function that represents the cost for the service during the first 5 hours as defined by the graph. Okay. F of x equals. We'll do this kind of squiggly looking thing here. Okay. Now, from hour 0 to hour 1, and you notice there's an open circle here and a closed circle here. Means it's not equal to 0, but it is equal to 1. So if you wanted to, you could go ahead and write 0 is less than x is less than or equal to 1. Okay. Let's clean that up a little bit. Oh, that's so much better, right? Alright. So from 0 to 1 it's 330. Okay. From 1 to 2 it's 550. But it's not equal to 1 on the second part. It's strictly greater than 1. But it is equal to 2. Okay. And then from 2 all the way to 5, it winds up being 770. So not equal to 2, but greater than 2, and less than or equal to 5. And there you go. So there's your piecewise defined function of this particular graph that they give you, 3.27. Easy enough. Like I said, it's really, really not that hard. Just take it piece by piece. The other thing we have to look at are absolute value functions. So an absolute value function, f of x equals the absolute value of x, is really the same thing as a piecewise function where f of x equals negative x if x is less than 0, and f of x equals x if x is greater than or equal to 0. So let me just put it really plain for you kind of down here in a minute. But just follow me as best you can here, and we'll do some examples that'll make a whole lot of sense. So if the absolute value of x equals a, and a is greater than 0, then x equals a or x equals negative a. Okay. If there is no solution to the absolute value of x equals a, if a is less than 0, while absolute value of x equals 0 has the solution x equals 0. What that means, essentially, is we can figure out what this x is. It's either going to be positive a or negative a. Okay, the x is inside the absolute value. There's no solution if you actually have a negative. So absolute value of x always has to be a positive number. There's no way to sneak it out and make it a negative number. So if you wind up with absolute value of x equal to a negative number, you're not going to have a solution. And if you have the absolute value of x equal to a 0, that means x has to equal 0. The only absolute value that gives you 0 is the absolute value of 0. So if we do these problems here, and I'll show you the method on how we plan on doing these. All you want to do is solve for x. To solve for x, what you got to do is x minus 3 equals 9, and x minus 3 equals negative 9. Okay, so follow me here. I'm solving for x. It's pretty easy to do. I add 3 to both sides. So here x equals 12. Okay, now I'm also going to solve for x on this one. So I'm going to subtract, or I'm going to add 3 here. I'm going to add 3 here, and when I get that, x equals negative 6. Now, what we're going to do is we're going to plug both of them in and show you that they work. So, change colors. So I plug 12 in. 12 minus 3, absolute value. 12 minus 3 equals the absolute value of 9, which is the same thing as 9. Okay, let's get rid of this little mark that I accidentally made. Okay, if I plug the other one in, negative 6, so I get negative 6 minus 3, and the absolute value of that. Negative 6 minus 3 is negative 9, so I get the absolute value of negative 9, which is 9. Okay, so you can see it works. So essentially, if you want to solve for x, but you got absolute value, you got to do 2 solutions. You got to do the positive solution, you got to do the negative solution. And it's that easy. Okay, so let's do this one. Same thing. 2x minus 4 equals 8. 2x minus 4 equals negative 8. And it never hurt to check your answers with these. So if I solve for this one, I get 2x equals 12, so that x equals 6. And here I get 2x equals negative 4, x equals negative 2. Okay. So plug 6 in here. 2 times 6 is 12. 12 minus 4 is 8. Absolute value of 8 is 8. I'll plug negative 2 in. 2 times negative 2 is negative 4. Negative 4 minus 4 is negative 8. Absolute value of negative 8 is 8. Simple enough. Let's look at C. Change color my pen again. Okay, so here what we've got the absolute value of x squared minus 5x equals 6. Okay, so let's go ahead and break this side up. So what we're going to get is x squared minus 5x equals plus or minus 6, essentially. Okay, so we really have to actually solve two equations here. We've got to solve x squared minus 5x equals 6. And we're going to come over here and we're going to solve x squared minus 5x equals negative 6. Okay, so let's get everything on one side with this one over here on the left. So I get x squared minus 5x minus 6 equals 0. I can try to FOIL that. Let's see if we can do it. Sorry, not FOIL it, but factor it. Let's try to factor it. We get an x and an x. Need two numbers that multiply to negative 6. Add to negative 5. How about minus 6 plus 1? Okay, so that tells me that x equals 6 and x equals negative 1. Okay, and if you need to set both of those equal to 0 and then solve, that's all I really did. I just jumped a few steps. Alright, let's solve this one. X squared minus 5x plus 6 equals 0. Okay, so you can try to factor this one as well. So I need two numbers that multiply to give me 6 and add to give me negative 5. How about negative 3 and negative 2? Easy as that. So that equals 0, which means either of those could be 0, in which case x equals 3 and x equals 2. Okay, so I have actually have four solutions here, potential solutions. Okay, now I'm going to take my pen here. Like I said, I'm going to change color. I don't know, we'll change it to black. Let's actually plug all of these in and see if they work. So we get absolute value of 6 squared minus 5 times 6 equals 6. 6 squared is 36. 5 times 6 is 30. So 36 minus 30 is going to be 6. Absolute value of 6 is 6. This one works. So we know that this solution is good to go. Let's check negative 1. So absolute value of negative 1 squared minus 5 times negative 1 equals 6. Negative 1 squared is positive 1. Negative 5 times negative 1 is positive 5. 5 plus 1 is 6. So that one works. Let's try these over here. Okay, we get 3 squared minus 5 times 3 equals 6. Alright, so we get 3 squared is 9 minus 15. That's the absolute value here. 9 minus 15 is negative 6. Absolute value of negative 6 is 6. So this one works. Let's look at the next one. So absolute value of 2 squared minus 5 times 2 equals 6. So 2 squared is 4. Okay, minus 10. Give you negative 6. Absolute value of negative 6 is 6. So all four work. Okay, so this one's actually going to have 4 solutions. Easy enough. Next thing we're going to look at is power functions. Okay, a power function is a function of the form y equals a times x raised to the b, where a and b are real numbers and b is not equal to 0. So in this example it says at 17 feet the wingspan of a prehistoric bony-toothed bird may exceed that of any other bird that ever existed. The animal weighed 64 pounds and soared the Chilean skies 5 to 10 million years ago. The wingspan of a bird can be estimated by using the model, and I hate this because every time I type this in it does this. Let me rewrite this for you. This was supposed to be up top, and every time I do this it freaking try to correct it, but it still does it. I don't know why. It's a glitch in the matrix. That's what it's supposed to look like. I don't know why it jumped down. Okay, so that's the equation we're going to use, where L is the wingspan in feet and W is the weight in pounds. Okay, A says compute the wingspan of a bird who weighs 40 pounds. Okay, so the biggest thing that you really need to go through here and find and make sure you know, matter of fact, let's just use this. So L is the, oops, thought I had the highlighter highlighted. Pretty certain I did. L is the wingspan, and then W is the weight in pounds. Okay, so it's important to keep those straight. Okay, so if we want to compute the wingspan of a bird that weighs 40 pounds, we're going to plug 40 in for W. So all we're really doing here, 2.43 times 40 raised to the 0.3326. And you should be able to type that in your calculator. The biggest thing is making sure that you basically type it in just like I typed it in here. Okay. So you'll do 2.43, hit the multiply button, 40, hit the up button, and raise it to 0.3326. Okay. I'm going to leave that to you on your own. No need to pull the calculator up for that. B says approximate the wingspan, or the weight of a bird whose wingspan is 11 foot 4 inches. Okay. So this is when it pays to know that the wingspan is in feet. Okay. So if the wingspan here is in feet, it gives it to me as 11 feet 4 inches. I can't just plug in 11 feet 4 inches. Okay. So that what I need to do is convert this 11 feet 4 inches into just feet. So there's 12 inches in a foot. So this is like 11 and 4/12 feet, which wind up being 11 1/3 feet, which is the same thing as 11.33 repeating. Okay, so that's what you'll actually have to type in here. So you'll have to do 11.33 equals 2.43 W. That is a very ugly W. Sorry about that. Still getting used to writing utensil. Raised to the 0.3326. Okay, so obviously what we're going to do to get W by itself here is I'm going to divide by that 2.43 to start with on both sides, which will leave you with 11.33 divided by 2.43, and you can approximate that if you'd like, and that equals W to the 0.3326. Now, like, okay, how do we figure out what W is now? Okay, so what we're going to have to do is we're going to have to figure out what W is here. Okay, and eventually we'll actually get into a really nifty way to do this with exponential and logarithmic functions. We're not going to work on that right now. Right now, all I'm going to show you to do, and I am probably going to take you to the calculator and show you this little thing. Okay, if I'm raising it here to the 0.3326, then what you can also do to get rid of it is you can take the root of it, but your root has to be a 0.3326 root. You have to do that to both sides. Okay, so let me go over to the calculator real quick and show you exactly how that works. Alright, so I'm over here at my calculator. I already took that 11.33 and divided it by 2.43. The next thing that I need to do is do the 0.3326 root. Now to do that, I'm going to hit the math button. I'm going to scroll down to number 5. Okay. And it lets you put whatever you want to right here. 0.3326, I believe is what it was. Let me double check real quick. Yep, that's it. And that'll be the root of, now I want this to go in there because it's 11.33 divided by 2.43. So I'm just going to go up, select it, hit enter, and it'll put it in there for me. Hit enter here. It tells me my answer here needs to be 102.3984905, wherever it asks you to approximate. In MyMathLab is where you'll approximate it. Okay. Now, like I said, if on that one before, if you had never used the up button, there it is right there. You can raise it to that 0.3326. That's for the previous one. If you've never used that up button, that's just how you use it. It's right there, just in case you needed to find it and was having trouble. But this 102.4 approximately is the answer to that last problem we just did. Alright, so as I said, the answer to this problem here, 102.4 pounds. Okay, so that's quite a big bird. A 102-pound bird that actually flies. That's insane. Next thing we're going to look at is root function. So a root function is a function of the form y equals a times x raised to the 1 over n, or y equals a times the nth root of x, where n is an integer and n is greater than or equal to 2. Okay, so in this example it says graph, and you've got these options here. So I'm going to go ahead and graph a, b, and c. So a says y equals the square root of x, or y equals x to the half. B is y equals the third root of x, or y equals x raised to the 1/3. C is y equals the fourth root of x, or y equals x raised to the 1/4. So let's go over to TI real quick and graph these, get this out the way. Alright, so the first one is the square root of x. Oops. So let's put that in y1. And x raised to the 1/2. Okay, and if I do a standard zoom on this, what I'll see is their exact same thing. If I come over here, clear this out, and I do the third root of x, so to do that I'll do math. You can use the third root of x, or x raised to the 1/3. You graph those, you'll see that those are indeed the same thing as well. And what you'll also notice with this is it looks a lot like the cubic function, just kind of laid over on its side. Alright, let's do the last one that we had here in the example, which was the fourth root of x. So if I do math, x root, I can put a 4 right here, I can put an x here, and that's going to be the same thing, honestly, as x raised to the 1/4. So you can kind of see that they're both the same thing by their graphs. And that's what this looks like here. So easy enough. Alright, so we have graphed all of those. You've gotten to see the graph of all of those. The other thing we got to look at is the reciprocal function. So we've got y equals x raised to the -1, or y equals 1 over x. So let's graph this one too. Something we'll notice when we graph to keep in mind, I'll go ahead and read through this and then we'll go to the graph. It says, notice the graph approaches but doesn't touch the y-axis. We said the y-axis is the vertical asymptote. Note also the values of y equals 1 over x get very small as the absolute value of x gets large. The graph approaches but does not touch the x-axis, so the x-axis is the horizontal asymptote. So we should have two asymptotes when we graph this, a vertical one and a horizontal one. So let's go over here to the graph and look at it. Alright, so if we do x raised to the negative 1 or 1 over x, they're going to be the same thing, but you can look at the graph and you can see. Just like we said, they get really close to the y-axis, but they never touch. It just continues to get closer and closer on both sides, up and down. And here, on the x-axis, this one gets really close to the x-axis, but never actually touches it. And you can see that if you zoom way in. And it does the same over here. So we got a vertical asymptote on our y-axis and a horizontal asymptote on our x-axis. And that's important to see for this and to know. Alright, the next thing we'll talk about is variation. So specifically direct variation as the nth power. So a quantity y varies directly as the nth power for n greater than 0 of x if there is a constant k such that y equals k times x raised to the n. Now the number k is called the constant of variation or the constant of proportionality. So if we look at this example 6, it says in the production of an item, the number of units of one raw material required varies as the cube of the number of units of a second raw material that is required. Okay, so what it looks like here, let's keep this with a pen. Let's keep this formula right here in mind. Okay, our base formula is y equals k x to the n. So I'm going to write it here, y equals k x to the n. Okay, that's our base formula that we need to keep in mind. That's what we're trying to kind of mimic and copy here. Okay, so if we read through the word problem really slow, in the production of an item, the number of units of one raw material, so our very first raw material, we'll call it y, okay, is required is it varies as the cube. So there's going to be a constant k in there, but it varies as the cube of another unit. So the cube means it needs to be a 3 here, x cubed. Okay. Now it says suppose 500 units of the first and 5 units of the second are required to produce 100 units of the item. Okay. So what we get here is we need 500 units of the first. Okay. And we need 5 units of the second in order to produce 100 units of the item. Okay, so what we get here, we're trying to figure out this constant of proportionality. So what we've got here is 500 equals, we've got to figure out what this k is. 5 to the third, 5 times 5 is 25 times 5 is 125. Okay, so if I want to figure out what k is, I've got to divide by 125 on both sides. Now 500 divided by 125 is just 4. So k equals 4. Alright, so what we have here is how many units of the first are required. The number of units produced requires 10 units of the second. Okay, so our new equation, if we want to rewrite it, is y equals 4 x to the third. Okay, so if I'm taking this part here, I know that we need 10 units of the second. So y equals 4. Let me rewrite that y because it's very ugly and it kind of looks like a 4. So y equals 4 times 10 of the second, so 10 to the third. Alright, so 10 to the third, 10 times 10 is 100 times 10 is 1,000. So y equals 4 times 1,000. Therefore y equals 4,000. Easy enough? Does it make sense? So your answer here, we need 4,000 units of the second. So 4,000 units. And that would be your answer for that. So that's how direct variation works. A lot of people get confused on this one because they forget that there's a K constant out front. You have to remember with direct variation that you have that constant out front. And typically what they'll do is they'll give you a kind of a proportionality to go by here to figure out what that constant is. Alright. Now if you got direct variation, you got inverse variation as well. So a quantity y is inversely proportional to x or varies inversely with x if there exists a non-zero number k such that y equals k over x or y equals k times x to the negative 1. So it's the same thing here, except this time the x is either on the bottom or raised to the negative 1, which is honestly the same thing. But you still have to remember that you got that constant out front. Okay. Also, y is inversely proportional to the nth power of x if there exists a non-zero number k such that y equals k over x to the n or y equals k times x raised to the negative n. So it works if you throw an exponent in the mix as well. Okay. Example 7 says the illumination produced by a light varies inversely as the square of the distance from the source of the light. If the illumination of 30 feet from a light source is 60 candela, what is the illumination 60 feet from the source? Okay. So we are looking, one, it says it varies inversely as the square. So we're really looking here at this formula. So that what we're looking at is the illumination I equals k over the distance d squared. Okay, so we need to figure out what this k is. Now it tells you if the illumination is 30 feet from the source, is 60 candela. So 60 candela is our illumination. Okay, still need to figure out what this k is, but we know our distance here is 30 feet. And we can solve for that k. Okay, so we need to figure out what 30 times 30 is. So 30 times 30 should give you, what, 900? And you can double, triple check me on that to make sure I'm right, but I'm pretty certain I am. So that you rewrite this as 60 equals k over 900. Alright, so if I want to solve for k, then I'm essentially just multiplying 60 times 900, which should give us 54,000. Okay, so that what I'm looking at here is I equals 54,000 over d squared. So I change colors here so that I can figure out what is the illumination 20 feet from the source. Okay, I equals 54,000 divided by 20 squared. Okay, so you type that in your calculator. 20 squared is 400. So 54,000 divided by 400 should give you 135. Okay, and you can double check me on that if you'd like to as well. Make sure you use your units here. So 135 candela would be your answer. So, and it makes sense. Always try to make sure your problem makes sense. So if the illumination 30 feet from a light source is 60, obviously if you get closer to the light source, it should be brighter, so you should have more candelas. So it makes sense that it would be 135. Okay, and that's as simple as it works. Okay, so biggest thing with this, go try your homework. If you have any trouble with your homework, let me know. If you have any trouble with the lecture notes, let me know. If you feel like I did something wrong, messed something up, it does happen, not too often. But send me a question about it and we can figure it out and see if I've done anything wrong or see what you did wrong. Okay. Other than that, like I said, jump on your homework, stay on top of things, and feel free to email me with anything you have.